And so we went through and came up with ways to identify what bonds are present in a molecule, then translate that into what forces. Okay? So we spent a lot of time in that process, and that's because if you can identify all that information, you can now predict a whole lot of properties that come out of this. Okay? So some of the big ones that you're going to be responsible for are our phase transitions. So this is looking at ultimately melting points, melting and boiling. Vapor pressure is a relation or related to your phase transitions, but you're less responsible for that one. We could predict something about viscosity. So how tight do those molecules hold? How honey-like they are, I guess we could describe it. Surface tension, same general idea, but you're not super responsible for it. The last one that you're going to be responsible for in your final will be solubility. Okay, so we will look at your phase transitions and your solubility in particular examples. If you move into, say, organic chemistry, that's when you then look at reactivity, being predicted from just interpreting forces and bonds. Okay? And what we talked about on Thursday, we went through really, really quickly. I guess I should undo that reactivity star. I'm not responsible for that one this class. We went through really quickly a way to kind of organize and interpret all of our bonds and forces. And so I put it all together in this one big wheel. Okay, the idea being is that when we're looking at the interactions between any two atoms, it is a spectrum, okay, much like a rainbow. And I split it into two rainbows because one side of that rainbow we'll look at as our bonds, the other side we'll look at as our forces. Ultimately, they are the same thing. We take any two atoms and we put them really far away from each other and we say there's no interaction whatsoever. As those atoms get closer to each other, they start to build some kind of attractive force. That force is now incredibly weak, and that places us in this London dispersion category. As we bring those atoms or change those atoms' characteristics, okay, their electronegativities, we can change the properties of that interaction. We can make it stronger. And so by making it stronger, we can move through our spectrum up to, say, dipole-dipole forces. If we make that interaction even stronger still, we can move up to hydrogen bonding, okay, a stronger force. As we continue to move, we're going to continue to make it a stronger and stronger attractive force. Okay, we get all the way up to ionic or electrostatic, and that is now our strongest force. As we increase that attraction between those atoms, we'll move beyond it being just a force and now into being a bond. It is now still a stronger force, but instead of it being intermolecular, where we're looking at two different molecules, we're now saying that that force is so strong it's become a bond. So now we're looking within the molecule. So it's intramolecular. If we continue to increase that attraction between those two atoms, we continue to move around our circle. And I know this gets a bit weird because we'll notice that we're starting to move down. It's still an increase in attractive force. Okay? But instead of it being classified as a force, we now reference it as a bond. So all we're doing is increasing the strength of that interaction until ultimately we reach the strongest attraction that we can possibly get, and we have a nonpolar covalent bond. Okay? Within that categorization, we want to be able to look at different subcategories. So our first subcategory of our interactions is forces versus bonds. Where our forces, sorry, it looks like it's up your nose. Where our forces are between different molecules. Okay? Things that are not actually bonded to each other or sharing electrons. Our bonds are now, we're saying that they're sharing electrons. Okay? That line between our bond and our force is a very, very thin line up at our ionic interactions. Because in one case, we're calling it an ionic bond. In the other case, we're calling it an ionic force. Okay? The next thing that we can go through and do is subcategorize each of those two categories as bonds and forces. So we end up with covalent bonds or nonpolar covalent bonds, polar covalent bonds, ionic bonds. When we move over to the forces, we can subcategorize it into three primary categories: London dispersion, dipole-dipole, and ionic or electrostatic forces. Okay. You'll notice that there is a fourth there. Why did I not say four forces to begin with? It's not quite that. Hydrogen bonding is actually kind of an important force.
Because it's a dipole-dipole?
Hydrogen bonding is technically a dipole-dipole force. So there's really only three primary categories, but we end up subdividing our dipole-dipole force into normal dipole-dipole and hydrogen bonding. Okay. So when asked for your forces, it's typically referenced as 4, but if you can remember that hydrogen bonding is really just a dipole-dipole force first, there really comes down to only 3. Okay, kind of makes sense? So the next part is then how do we use this information? Sure, we can look at a molecule and say that we have a polar covalent bond or an ionic bond. For instance, done that example too much. Let's do potassium bromide. What kind of forces would I expect between potassium bromide and, say, a second molecule? What force should show up there? Okay, ionic. How do you know ionic?
Because they're ionic.
First, we look at the bond and our potassium bromide. What type of bond do we have there? It's an ionic bond, and we know it to be ionic because metal and a nonmetal. If I have an ionic bond, that suggests that I'm going to have an ionic force. Okay. How would I know for sure that it's an ionic force? I then also have to classify what that other molecule is. Okay. But what we're doing is really quickly evaluating the bond structure within our compound and then saying what could it potentially do as the strongest interaction for the next thing. Kind of makes sense? Okay. When we look at our phase transitions, okay, which is really our melting points or our boiling points, if we take, say, our compound KBr and we compare that to another compound, not particularly creative this early in the morning, I guess. All right, let's do silicon tetrahydride. Okay. I want to be able to do some kind of predictive ability of my melting points and boiling points. Okay. Which of these would have the higher melting point? Okay. What is a melting point? Okay. It's the phase transition going from solid to liquid. To melt a compound, what do you have to break? Careful. Don't break bonds. You speed up the molecules to the point that you break the attractive force between individual molecules. When you melt a compound, very rarely are you actually breaking bonds. You're breaking the force connecting individual molecules with each other. Well, what is the attractive force between a KBr molecule and another KBr molecule? Electrostatic. I don't have enough space to write that, so I'm going to stick with ionic. What kind of force would we get between silicon hydride and another silicon hydride? Right. We're likely looking at a dipole-dipole force, just based off of our rules of thumb. Questions on determining the dipole-dipole force? Do you think you got that? Okay. Which of those two forces is stronger, ionic or dipole-dipole? Ionic, which means KBr molecules are holding with a very strong force against each other. What does that mean as the amount of energy that I need to put in to get those molecules to break away from each other? I need more energy. Well, if I have to put more energy in, what happens to the melting point? It goes up. Okay? So by understanding something about what we're looking at, so you have to know what a melting point is. What is physically happening when we look at a melting point? What is physically happening when we move to solubility? You can then use bonds and forces to predict something of those properties. Kind of make sense? Hi. Let's test you on that. Could make this a quiz. That was a bad idea. It's not a quiz. Okay. Tuesday before Thanksgiving, no one's going to show up. Okay. Spend some time, go through, take a look at these, and decide which compound within each pair, so you've got 4 pairs here, which compound in each pair should have the higher melting point. Higher melting point means what? Stronger or more energy. I'll stick with that. Which means what about our forces? Which means a stronger force. Which means a more ionic bond. Okay. This is a little bit trickier because when we look at each of these molecules, is there only one bond type? No. So you've got a bunch of different bond types within these. Use that information based on our more energy, stronger force, more ionic bond. And try and classify between those pairs which compound should have the higher melting point. And do, ooh, I don't know how far back I have to go. So we'll split this into 2 columns here. You have forces on the left. Let's just erase that title altogether. And on the right, we will put in the bonds. Okay. What are the types of bonds that are possible? Ionic. An ionic bond is a legitimate bond. Right? If I have a compound with ionic bonds, say sodium chloride, if I now see how it interacts with a second molecule of sodium chloride, how does it interact? Top interaction or the bottom interaction? Top. Why the top? We're trying to neutralize the charge between those. So that top interaction is our favorable interaction. Okay. What type of force is now between those 2 ionic compounds? Electrostatic, or we reference as ionic bonding. Okay, which I know is weird because we're referencing a bond and a force at the same time. Okay. So if we have an ionic bond, we lead to an ionic force. So here we'll call this an ionic bond. If I can identify that I have an ionic bond, I have ionic forces. How do we know we have an ionic bond? A metal and a nonmetal. You have to have that memorized. Okay? Which you technically already have memorized from Chapter 3?
I don't know.
I mean, it's possible. I was going to say Chapter 6, your nomenclature chapter. How do you name compounds? You had to recognize ionic versus covalent. You have to be able to recognize ionic compounds for naming. Okay? Whether you do is a separate issue. Okay? But that's what you're responsible for. After we've got ionic bonds, what other type of bond do we have? Bond. So London dispersion is a force, not a bond. I know. We have polar covalent, which is not a bad one to come up with because it is a perfectly valid bond classification. Though I'm going to make the argument that that's going to be a very hard one to work with at this stage. Okay? Because how do you know you have a polar covalent bond? What's our rule of thumb? Everything else. Okay, well, if we've only got 2 bond classifications, one is metal and nonmetal, and the other one is now everything else, we really only have 2 categories. Okay, so that becomes a bit difficult to classify a compound with just these 2 definitions. So the last bond type, I'm going to put it in parentheses for the nonpolar part, covalent. Okay. How do we know we have a nonpolar covalent compound? two nonmetals isn't going to help us out. It's technically true, but that's not going to help us out. What was that? Hydrogen to carbon. And anything to itself. Okay, so those are our two definitions for our nonpolar covalent. Now our polar covalent bonds make sense, because now it's everything else. So if it's not ionic and it's not nonpolar covalent, it's polar covalent. Now I can work with it. If I have a nonpolar covalent bond, like carbon to hydrogen, which interaction is favored? Top or the bottom? Doesn't matter. Okay. Would I expect there to be a strong force? There shouldn't be any real strong force. There's a strong force in the ionic bond because I'm neutralizing charge, a positive and a negative. A negative chloride with a positive sodium. When I move to the nonpolar covalent bond, what charge builds on the carbon? As a hint, it's nonpolar, which means no poles. What charge builds on the carbon? 0. There is no charge on that carbon. There is no charge on that hydrogen. The reason we don't have a favorable interaction between these two sets of bonds, or two sets of molecules, is that there is nothing to stabilize. There's no reason for each of those molecules to interact with each other, because there's nothing to neutralize. Well, if there's nothing to neutralize, should that interaction be strong? No, there's no reason to interact. Okay. If there's no reason to interact, we have an incredibly weak force. The initial pass at looking at these forces says that it is so weak that we completely ignored it. Some famous smart aleck came along and said, you know what, it actually is important. And because we said initially that it was completely irrelevant and they've proven us wrong, we then name the force after them. That's where the van der Waals name is coming from. Okay. London dispersion happens to be the more common name because it starts to apply a little bit more about where it's coming from. But that is now our incredibly weak force. So if I have a nonpolar covalent bond, that is going to directly lead to a London dispersion force. This leaves me now in kind of this weird gray category. I got polar covalent being everything else, and that's going to now lead to what force? Okay, well, technically it's going to lead to everything else, okay, whatever's left. Officially, it really leads to just the dipole-dipole force. Okay. So how do we get hydrogen bonding? Hydrogen bonding is a dipole-dipole force. So if I have a polar covalent bond, I then look to say, oh, I've got a dipole-dipole force. If I now have a dipole-dipole force, do I have the extra rules to say I have hydrogen bonding? What are the extra rules for hydrogen bonding?
Hydrogen bonds to...
I need a hydrogen bound to fluorine, oxygen, nitrogen. There's somebody that remembers some phone. These doors opening and closing is killing me, by the way. It says bound, not bonding. I'm really trying to emphasize that this is a hydrogen physically connected through a bond to fluorine, oxygen, or nitrogen. Hydrogen bonding is not a bond. It is an attractive force. Right? So we got the rough idea on being able to classify those now. Which is our strongest force? Ionic. Our weakest force? London dispersion. When we move to our melting points, a higher melting point means a stronger force, which necessarily means more energy, which I would actually put higher up on that category. So we'll just say more E up there. What does that mean for our bond? So I heard someone say stronger bond. It's more ionic. It's not a stronger bond. The ionic is the weakest bond. Nonpolar covalent is the stronger bond. I know, it's all sorts of weird. Right? Our strongest force comes from our weakest bond. Right? I know, that's bizarre, but that's how it works. Right? So instead of memorizing it as stronger bonds, say stronger force, which then means a more ionic bond. So we'll do these now solved in reverse order, because I said number 4 was easier than 3, easier 2, easier than 1. We take a look at number 4, 4a. What are the bonds found in that compound? Okay. I heard polar covalent. Everybody okay with me writing PC? Okay. Where's the polar covalent bond? Oxygen and hydrogen is a polar covalent bond. What other types of bonds do we have? Sorry? Nonpolar. We have nonpolar bonds between, we'll say NP, between our carbon and hydrogen, and between our carbon and carbon, we also have nonpolar. We also have between the carbon and oxygen, polar covalent bond. In our classification, we said more energy, stronger force, more ionic. So my ultimate goal here is to find the strongest force in this molecule. A nonpolar bond generates what type of force? London dispersion forces, which happens to be the weakest bond, or weakest force. Okay. That technically classifies, I didn't say that loud enough for you to hear. Don't read the words coming out of my mouth. Okay. What about the polar covalent bond? What force does that lead to? Dipole-dipole. I'm trying to find the strongest force in each molecule. What is the strongest force in 4A? Dipole-dipole. And actually, I'm going to undo that. I'm going to box the other one. But I'm not going to explain why. We'll deal with it in the next question. We can then move to 4B. In the process of looking at 4B, what do we find? Nonpolar, nonpolar, LDF, LDF. Carbon-oxygen, we have polar covalent, dipole-dipole. And the last one, oxygen and sodium, we have ionic, which leads us to electrostatic or ionic, depending on our definition. Which is the strongest force in that compound? Our ionic. Between these two compounds, which one has the stronger force? One on the right, 4B, which means higher melting point. Okay. What happens when we move to 3? Or before we do that, questions about that? Okay. What happens when we move to 3? Can I erase everything there? I just need the space to write again. I accept that. We move up to 3, we'll do the same categorization. Carbon and hydrogen, what do I have? Nonpolar, which leads to London dispersion forces. Carbon and oxygen, what do we have? Polar covalent, which leads to dipole-dipole. The oxygen and carbon on the other side. Polar covalent leads to dipole-dipole. And carbon-hydrogen, nonpolar LDF. What's our strongest force? dipole-dipole. Versus the next compound over. Same idea. Want to work through and do that. Carbon to hydrogen. Nonpolar, LDF. Carbon to carbon. Nonpolar, which leads to LDF. Do I need to do it in the next carbon to hydrogen? No, we've already identified LDF as a force from our nonpolar covalent bonds. Looking at the next carbon to hydrogen, it is going to generate the same force, so why bother? Okay. How about carbon to oxygen? Polar covalent, which leads to dipole-dipole. Oxygen to hydrogen. Polar covalent, which leads to dipole-dipole. Comparing our melting points between these two compounds, we pick our strongest force. In 4A, it was dipole-dipole. 4B, dipole-dipole. So we could go through and say, well, this is an impossible question. We get the same force. Are the dipoles identical to each other? No. There is a difference between these dipoles. If you can see that there is a difference between the dipoles, there is a difference between the melting points. Okay? So you still need to be able to identify that difference. What is that difference? Ultimately, it comes all the way back to electronegativity. Okay? The difference in electronegativity between hydrogen, the least electronegative nonmetal, and oxygen, the second most electronegative element, is now massive. It is such a massive distance or difference between those two that it becomes an incredibly big dipole, which means instead of referencing it as just those standard little d's, we can call it, this is going to come out really wrong, but I kind of have to say it, as massive double D's. Sorry. Bigger dipoles means stronger force. That force has actually become so strong that what do we then classify it as? Hydrogen bonding. How do we know it's hydrogen bonding? We have a hydrogen, we have a dipole-dipole force, and we have a hydrogen bound to oxygen, which means I have hydrogen bonding. Which is the stronger force, hydrogen bonding or dipole-dipole? Hydrogen bonding. If compound 4B has the stronger force, what does that mean? Higher melting point. Make sense? Right. We good with everything up there? That was not the eraser I meant to use, but it works. Question 2. What's the bond type between carbon and hydrogen? Nonpolar. Carbon and carbon. Nonpolar. Carbon and hydrogen. Carbon and carbon. Carbon and hydrogen. Those are all nonpolar bonds. So since there's no difference between them, we can just classify the whole thing as nonpolar, which leads to what force? LDF. When I move to the next compound, I can go through and do the same classification, looking at every single bond and classifying it. Or what I can start to go through and do is say, since I'm trying to rank these two, I'm trying to find a stronger force. So instead of looking for the absolute crappiest bond, I should look for the strongest or most polar bond. Well, the most polar bond, we would expect to find what? Most polar bond needs a metal to be an ionic bond. Do I have a metal? No. What should be the next thing I look for? Okay. I could immediately jump to my nonpolar covalents. Okay. And by looking at this, I should say carbon to hydrogen, nonpolar covalent. That's the same as the other one, so I don't care. I'll ignore it. And I'll move on to the next one. Oxygen. Oxygen to carbon is what type of bond? I have a polar covalent bond, which then means dipole-dipole force. Which of these should have the higher melting point? 4B, because it has the stronger force. Okay. So each of those little steps that we went through and looked at every single bond is something that you should start to internalize. You shouldn't have to write that out every single time. If you've got time on a test, absolutely do it, because you now have something to work with. Okay. But these are things that you should be internalizing quickly. Questions on number 2? Yes?
Wouldn't we say that it's the strongest force, I guess, is the hydrogen bonding?
Is hydrogen bonding? Is there hydrogen bonding in molecule 4B? Okay. I do have a dipole-dipole, or I do have a dipole-dipole force between that oxygen and, say, the carbons. Okay. So if we go through and look at any one of those bonds, the attractive force there is dipole-dipole. For it to be hydrogen bonding, what does the first atom need to be for that oxygen to interact with it? Hydrogen. What is that hydrogen bound to in this molecule? Carbon. Is that interaction hydrogen bonding? Why not? So we got a couple answers. One was it's not fun. No fluorine, oxygen, or nitrogen is connected to that hydrogen. Okay? I would argue that you shouldn't even get to that point. Before you can get to that point, you have to first identify a dipole-dipole force. The CO bond for sure generates your dipole. What does the HC bond generate? It's a nonpolar covalent bond. It gets you London dispersion forces. Is the attractive force between those molecules dipole-dipole? No. It's dipole-London dispersion. Is that such a bond or such a force? That does exist. It's now just between two different molecules. But would I expect that force to be as strong as a dipole-dipole force? No, because I don't have the other dipole to neutralize that charge. Okay. Why did we not look at this type of interaction as its own subcategory? Do you really want to look at all the possible subcategories there are? No. We picked the bulk ones because those are easier to work with. Okay? So no hydrogen bonding in that molecule. Other questions? Okay. Now arguably for the hardest one on this, number 1. What bonds do we get in that first 4A? Nonpolar, which means what force? London dispersion forces. And the next one, what bonds? Nonpolar, which means LDF. Which compound should have the higher melting point? I got the same forces. Uh-oh. Why should 4B have the higher melting point? You started to say something? Okay, we'll go back to you, just because you both said something.
Because it's more energy to break up the bigger compound.
The bigger the compound, the more it's going to interact with other compounds. Even if it is a weaker force, it is going to interact more, because it's bigger. Okay? If a fly comes up and bumps into you, you probably aren't that bothered. But if I came up and bumped into you, you'd probably be a little bit bothered, particularly if I'm moving at the same speed as a fly. Okay? You're not going to be particularly happy about that. Why? There's more of me to interact than there is of the fly. Same thing's happening here. There is more interaction between the larger molecule with other like molecules, which means if there's more interaction, there's now more things that we have to break to get it to go into the next phase. Kind of makes sense? So when we look at our melting points and boiling points, our first pass, which has the strongest force. Our second pass is the amount of forces. Okay? You'll deal with potentially the third and fourth pass when you move into, say, organic chemistry. We don't need to worry about that here. As just a quick, fun little test on this. Every point is a carbon on this structure. I just don't want to draw all those carbons. What is the strongest force that we would get out of methanol, CH3OH? Hydrogen bonding. Okay, so you're already starting to skip through some of those steps. It's a good thing. We've got a hydrogen bound to oxygen, nitrogen, and fluorine. So the strongest force I would get for that compound would be hydrogen bonding. How about the next compound? So every point is a carbon. So we've got a structure that's just full of carbons and hydrogens. Just carbons and hydrogens. It's going to be nonpolar bonds, which means London dispersion forces. Which of these two compounds would we expect to have the higher melting point? The one with hydrogen bonding. We would expect methanol to have the higher melting point because it has the stronger force. Methanol, anybody know the phase? Liquid. Okay, not a bad guess, but it's a liquid. This compound is known as naphthalene. Anybody know the phase? It's a solid. Okay. This is a bit odd because if we look according to our rules, our strongest force should have the higher melting point. The strongest force here is hydrogen bonding. But as we just did with A and B, what happened with number 1, A and B? The more molecules we or the more atoms we had in our molecule, even if they were nonpolar covalent bonds, we had more forces. More forces meant a higher melting point. When we move to this comparison here between methanol and naphthalene, what's going on? Naphthalene is so much larger. Even though it has weaker forces, it has a lot more of those weaker forces. Okay. Which is easier to break? A 2x4 or a piece of spaghetti? Okay. A piece of spaghetti is pretty easy to break. It's a relatively weak attraction. But if I take that 2x4 and now take a whole bunch of spaghetti and try and break all the spaghetti at once versus the 2x4, it now starts to become a little bit easier to break the 2x4. Okay. So it's the total of each of those interactions that makes it more difficult. How do you know how much you need? You don't. Okay. That's where it comes into the real world, and you would start to come up with an approximation, see what happens. That's what you would work with. What you can expect on your test, these kind of molecules. Keeping it relatively simple, 2, 3, and 4 are your good classifications for your test. Make sense? Wow, you spent nearly an hour doing that one slide. This means you guys are awesome at it? Okay. Phase transitions. I just kind of want to mention this just so you're aware of it. It's not a huge issue. Temperature and heat. Let's pick ice because it's a nice straightforward compound. Let's pick ice at a really cold temperature. What's a really cold temperature?
Absolute zero.
Absolute 0 is a little too cold for me. 0 degrees. And 0 degrees is a little too warm.
30 degrees.
Let's pick negative 10 degrees Celsius. What happens as I start to add heat? Not quite. If I just have ice sitting on its own and I always start to heat it up, what happens to the temperature of the ice? It'll go up. Okay? As we add heat, and it's a little bit harder for us to see with the ice, so when we move into the liquid phase, it'll make a little bit more sense. So as I move along the x-axis, I would expect the y-axis to go up as well. So I'm increasing the temperature, okay, of my ice. Until eventually what happens? What happens at the phase change? So at now 0 degrees Celsius, what happens? It flattens out. Why does it flatten out? Why does ice not go from, say, 0 degrees Celsius to 1 degree Celsius? What is that 1 degree Celsius? Liquid. Okay. But if I'm at 0 degrees Celsius, am I at a liquid? No. I'm somewhere in between a liquid and a solid. To get it to move into the liquid phase, I have to provide it enough energy that it can now start to mobilize and move. So what will happen is my energy or my heat versus temperature will now level. Okay? And it's going to flatten out until what happens? Until all of it has transitioned into the other phase. Now what happens is I add more heat. The temperature increases. And it'll go from 0 degrees Celsius water to 1 degree Celsius, 2 degrees Celsius. So it'll start to go up again until what happens? We hit another phase change at 100 degrees Celsius. And once I hit 100 degrees Celsius, what happens? You're boiling your pot of water, you hit 100 degrees, poof! It's all a gas? No. What happens? That would be kind of scary, by the way. You don't want that. It boils. It begins to transition from the liquid to the gas. Do you still have to provide energy to get it to do that? Yes. What happens to your energy diagram or your heat versus temperature? It plateaus again. Until eventually what happens? It becomes all gas. And now what happens as we add more heat? Not quite yet. The temperature goes up, just as before. This is kind of a common misconception that a lot of people have when we think of gas phases. If you've got steam flowing through a pipe, you say, well, be careful of the steam. Well, it's only 100 degrees Celsius. No. Typically, steam flowing through a pipe is a lot hotter than 100 degrees Celsius. We can heat that sample up, or that gas, an incredibly high temperature because there's now no intermolecular forces to break. The limit of adding heat is now going to be, as you suggested, when you're actually breaking the individual molecules apart from each other. Okay, you're breaking the bonds. That requires a massive amount of heat. So if you see a steam pipe, that temperature is anywhere from 0 degrees to probably several hundreds of degrees. So we don't want to break those open because that would suck. Okay? So when we're looking at this, all we're trying to say is what is happening at each case. As we add heat, our temperature will go up until we reach our phase transition. We are still adding heat. That distance, okay, that difference right there, the amount of energy I had to put in, is now the energy to do what? Phase change. Okay. In this case, it's what phase change? Solid to liquid. So if we're going in the solid to liquid direction, this is our energy for, there it is, melting. What if I looked at the reverse direction? That would be now my energy for freezing. What is the relationship between the energy of melting and the energy of freezing? They are the inverse of each other. Okay. Said another way, the energy of melting plus the energy of freezing must equal 0. Also known as our conservation of energy. That was chapter 3. Don't test me on that. I think that's true. Okay? So what we're just looking at is how those things transition. When you move into 151, guess what you get to do? All sorts of fun calculations involving what temperature it is, how much heat you have to put in, interpreting ultimately this graph, okay, with all the quantifiable numbers and stuff like that. Okay? Questions? Okay. So when we are now at those phases, what we are or at those, and now I can't go back, those plateaus, is those plateaus are adding energy in to break the forces, break the molecules away from each other. That's what's happening at our melting point and our freezing points. If we switch to a new property, solubility, aka miscibility, okay, we're looking at how two liquids mix with each other when we're looking at miscibility, and solubility is two anythings, okay, dissolving in a liquid. Okay? Rule of thumb on predicting, is it soluble or is it not, is this term like forces dissolve like forces. Okay? So what does that mean? Well, we look at our individual compounds and we'd say, what is the strongest force in this compound? And we look at the other compound and we say, what is the strongest force in the second compound? Are those forces similar to each other? If they are similar, what does that mean? They mix with each other. They would be soluble or they would be miscible. Okay? So let's take a look at a classification here. H2O, what is our strongest force? Hydrogen bonding. Next one, anybody recognize that compound? Ethanol, alcohol. What is the strongest force in that compound? Is hydrogen bonding similar to hydrogen bonding? Yes. What does that mean? They should mix. Is that true? I know nobody would ever drink ethanol in your solutions. Beer, 5% alcohol, 5% in what? Water. Yes, they mix with each other. Okay? Almost perfect proportions. Okay? What happens when we move to the next compounds? Our strongest force in hydrogen or the water was hydrogen bonding. Our strongest force in that next compound, propane, LDF, London dispersion forces. Is London dispersion similar to hydrogen bonding? No. Would I expect those two to mix? No. That's it. That's all solubility is. You look at the forces, say, are they similar? Yep. Okay, they mix. Okay. At its most simplest level, that's what you are responsible for when it comes to solubility. So you have to look at a compound, look at that formula and say, these are the bonds, which then means these forces. Now I have something to compare. You move to the other compound, and you say, what are the bonds? That means these forces, are those forces the same? If they're the same, soluble or miscible. If they're not the same, insoluble or immiscible. Yes?
Was there any crazy link exceptions?
Are there any crazy weird things that could possibly happen with this? Yes. H2O, what's our force? NaCl, what's the force? Ionic. Are those the same force? No. Are they similar? Okay. So you actually know the answer to this. I'm positive you know the answer to this. Sodium chloride is salt. What happens when you add salt to water? It dissolves. So you know the answer. Okay. Because you know the answer, how similar are ionic and hydrogen bonding? Similar enough that they mix evenly and it dissolves. Okay. There is a special process that is happening within water and salt compounds, or most ionic compounds, that if you see an ionic force, that makes the entire compound soluble in water. Okay. Hydrogen bonding is such a strong force that it ends up equating very similarly to your ionic force. Okay. What happens the other direction? What if we said water and, hydrogen bonding and a compound that had dipole-dipole as a force? Well, now what? Miscible, immiscible? The weird frowning face, I don't know, is a good answer. Okay. When it comes to solubility, very often it is a guess. That is what we're looking at. There's a reason it's called a rule, in quotes, of thumb. Okay? Because plenty of people cut off their thumb by accident. The same thing happens with solubility. Sometimes it just doesn't work very well. I have no idea. It's close enough. Okay? What you are responsible for are the big extremes. Okay? Where you can run into some gray areas is we can change the question of being which of these compounds is miscible to which of these compounds is the most miscible. Because now it's a comparison. So if I had, say, water, and I gave you a compound that was, let's do it up here with the top. Make a real quick change to this guy. Change this to CH3O, CH3. Which compound is more soluble in water? CH3OCH3, call that compound A, or propane, compound B. Which one is more soluble in water? Okay. We look at our forces. A does not have hydrogen bonding. It has dipole-dipole, right? So that's not the same force. We look at B, hydrogen bonding versus LDF. Also not the same force. But which one is closer to being like hydrogen bonding? A. Okay. You can't have hydrogen bonding without dipole-dipole, which suggests A is going to be more soluble. And the answer is A. Okay. So do the best comparisons you can when in those situations. Kind of make sense? Okay. Water and solubility. Yeah, I do have a little thing here on this. So if we're looking at water, waters are kind of standard molecule. This is straight out of our textbook. We have a large partial negative on our oxygen, large partial positives on our hydrogen. If we go through and apply that to all of our molecules, we would expect a strong interaction between those molecules. And that interaction is now hydrogen bonding. And just to be particularly irritating, what is that interaction? Covalent is a good, safe answer. It is a bond. Which type of covalent bond? Nonpolar or polar? Polar. It is a polar covalent bond. Any ideas what I might have been trying to fish for there? A hydrogen bond, because it's a hydrogen bound to an oxygen, right? It's not a hydrogen bond, it's a polar covalent bond. Your hydrogen bonding interaction is a force between separate molecules. Okay? Kind of makes sense? Why do our ionic compounds dissolve in water? If we take an ionic compound, when it hits water, it turns into sodium ions and chloride ions. It now has to interact with water. By definition, it must. Okay, if it's going to dissolve, it's got to somehow interact with water. What atom should I be placing in that box? Hydrogen or oxygen? Since you said oxygen, what charge does our oxygen build? Charge does our oxygen build? Negative. What happens when the partial negative gets near another partial negative? They repel. Is that going to be a good interaction? No. Okay. So what atom should I be putting in there? A hydrogen. I now have an interaction between those charges. One is ionic, one is a dipole. How strong of an interaction is that? LDF strong? No, it should be stronger than an LDF, right? Because we have an ionic charge and a dipole charge. Stronger than dipole-dipole? Yeah, because we have that ionic charge contributing to it. Stronger than hydrogen bonding? Yeah. So it is a pretty strong interaction. Is it stronger than an ionic interaction? No. Well, in the solid, we would have ionic interactions, sodium chloride with other sodium chlorides. So to dissolve, I have to make an interaction that is more favorable than it is in the solid. Well, I just said this interaction is weaker than in the solid. Well, if it's weaker, it shouldn't dissolve. What else is happening in this solution? What atom should I put in this box? What charge is the oxygen? Or sorry, the chlorine? Negative. What atom should go in that box? A positively charged atom. What positively charged atom should I put there? Hydrogen. How about in this box? Hydrogen. How about in another box? In another box. Hydrogen. I'll address that in a second. When we go through to dissolve our salts in water, we can put a lot of water molecules around an individual ion. So while we are generating a weaker force, the sum total of those interactions is now a stronger interaction than the 2 or 3 interactions we would get in the solid. Okay. That is what allows salts to dissolve in water. It creates a solvation sphere, as it's known, where water interacts with that center molecule, and we have tons of water molecules there stabilizing and lowering the overall charge on the chloride. Could I draw a sodium there? Yes. But by drawing a sodium in one of those boxes, I am saying what happened to the solubility. It didn't dissolve, because it's still sodium chloride. When it dissolves, we have to break that interaction for a salt. Okay? All we're trying to get at is that those similar forces, sometimes you have to look at how many of those similar forces are happening, not just saying it's one interaction. So it's not always crystal clear and clean. Questions? Okay. So we now have compounds that have dissolved in water. If I'm going to run a reaction, say like the reaction up here, I can take the compound aluminum bromide and I can dissolve it in water. And I can take the compound silver nitrate and I can dissolve it in water. If I now want to run a reaction between these two and predict products, what do I need to know about the aluminum bromide and about the silver nitrate to predict how much product I get? How many are present? How many aluminum bromides are present? Okay, well, can you count them? No. So how did we determine previously how many, how many aluminum bromides are present? How did we measure that out before? Moles. So you went into the lab and you counted each and every single one of those molecules. Mass. So measure the mass of aluminum bromide aqueous. Are you going to be measuring just aluminum bromide? What are you measuring also? Water. So you can't get away with mass. We need some other way to measure it. Okay? We need to know how much of that aluminum bromide is present in water. How do we do that? You could make the solution, but making the solution is not particularly easy. Those of you in lab, yes, I'm using you as shields. Those of you in lab, we've come up with a way to measure. How did we measure in lab? Nope. With our last lab, what did we do? Titration. How did we know how much base was present in the solution? No. Your indicator told you when it was basic. How did you know how much, how many moles of base were present? We needed to know the concentration. What units did we use for concentration? Molarity. Our moles for the volume of our solution. That's what we're introducing with this concept. It is the molarity of your sample. How much of that compound is present in the water solution? Okay. So with our molarity, we now have a way to relate that, which is lovely because we always go through and refer to it as our molarity, and we give it a special unit. What unit do we end up using? Big M. How many times have we ever used big M in any conversion? We haven't, because it's dumb. Instead, we should think about big M as moles per liter. So what is our concentration really give us? Moles per liter, which is ultimately a conversion factor that allows me to then measure out the volume of each of those solutions. Once I know the volume and its molarity, I can then determine the moles, which is the how much of each of those species I have. Once I have how much of them, I can then use the balanced equation to predict how much product is being made. Okay? Let's see. So what is the molarity of a solution containing 24.0 grams of sodium hydroxide and 0.1 liters of solution? You guys want me to solve this one for you and then make you work on the next one? Okay. Good, because the next one's harder. Molarity is what? Moles per liter. Okay. That is what we're trying to get to, so I should be writing that on the left-hand side of my slide here. Do I know the moles of my sample? No. What do I know about my sample? I know I have 24.0 grams, okay, of sodium hydroxide. Do I have the volume of my sample, the liters? Yeah. Okay, where do the liters need to show up? So I heard on top and I heard on bottom. Which is which? It needs to show up on the bottom because it shows up in the bottom. That's where it is. Okay. 0.100 liters. Are grams per liter the same thing as moles per liter? No. So what do you need to do? You need to convert. Grams needs to show up on the bottom. What do I want on top? Moles. Grams of what? Sodium hydroxide. Way to use your nomenclature there. Do I have a conversion factor between moles and grams? Where's that conversion factor found? Periodic table. Sodium 23, oxygen 16, hydrogen 1, 17 and 23, 40 grams per mole. I think that's right. Where does the 40 show up? In front of grams. What do? Cancel units, punch it in the calculator, I now have the answer. Okay. You place your variables where you want them to show up. Okay. Why can I do grams over liters at the very beginning? Because that's what I know I need to get to at the end. Okay. All it's now trying to do is a setup of unit conversions all the way through. But in those last couple minutes, how many grams of potassium dichromate are in 125 milliliters of 0.50 molar solution? I'll get you your skeleton set up, and then you should try and crank it out. What is it, K2CR207? as a hint, I would argue 3 conversions.